carbon inside of this steel. As we know steel, it's a mixture of air and carbon. So initially, it has carbon concentration, which is CO equals 0.25 WT%. What is WT% again? Quick review here. We learned WT% and AT% from chapter 4. That's called weight percent. How to calculate weight percent? That's when you have mass divided by the total mass times 100%. That's weight percent. Okay, the initial concentration of carbon, it's 0.25 weight percent. And so that's what is inside of this lumbar, CO, or C naught. And this bar is at temperature of T equals 950 C Celsius. And on the left end of this bar, this steel bar, it's exposed to a high carbon concentration atmosphere. So on this end, we have very high concentration of carbon. In this case, we have CS. It's 1.2 weight percent. So that's a surface concentration. That's a boundary condition. And CO, it's an initial condition. CS. Remember, both CS and CO are the concentration of carbon. Okay, another information we know is the diffusion coefficient. D equals 1.6 times 10 to the negative 11th meters squared per second. So this is the diffusion coefficient when you have carbon diffused into the steel. Remember D, that value, it depends on the temperature and the materials. All right, those are the given information. And what we need to find is, we want to find out how long it takes to achieve a carbon concentration of 0.8 weight percent at a certain location, which is x equals 0.5 millimeters. So find how long Okay, our goal is to find how long it takes to achieve a carbon content of 0.8% at location x equals 0.5 millimeters. So x equals 0.5 millimeters. Let's see, it's about right there. That's 5.5 millimeters. Actually, 0.5 millimeters is very tiny, right? If you just, well, it's kind of like the same size, same radius of your pencil lid. It's 0.5 millimeters. So this is a real engineering application. That's how we want to harden the surface of a steel. So imagine we talk about that in the impurity. If you have more and more steel in more and more carbon content in your steel, that increases the yielding strength, make your steel harder. So that's why a lot of like gears, they want to do the same procedure, put gears inside of a very high carbon concentration atmosphere in order to increase the surface strength. So same deal here. And we want to figure out at this location, how long it takes location to reach concentration of 0.8%. Right now, remember the initial condition we have is inside of this bar, we only have 0.25 weight% of carbon. Now we want to increase that to 0.8%. Not 0.8% everywhere, it's just 8% at that particular location. Since only one end of this bar is exposed to the high concentration carbon, imagine that carbon concentration will increase start from the left end and gradually move on to the right of that bar. So it's not instantaneous, it takes time. Our job is to figure out how long it takes. Can we just give a guess? We're increasing the concentration of carbon from 0.25 to 0.8%. Let's give a reasonable guess how long it would take. Minutes, hours, days, months, or years? Just give a guess, wild guess. Anything. Days, 6 months. Any other answers? 2 years? Okay. All right, let's do the calculation to see how long it takes. But keep in mind here, the temperature is really high here. The temperature T is 950 Celsius. That is about, we have a number here. Never mind. That is about 1,750 Fahrenheit. So temperature is pretty high. Like we mentioned, everything in this course is related to temperature. If you have very high temperature, that means the diffusion gonna occur very fast as well. But we mentioned for solid, diffusion is always very slow. Okay, now let's see how can we use those given conditions and use this, our magic solution here, to find out what is time t. That's a variable we're trying to find out. So can we, first, let's list everything we know. Solution. Here we know CO, which is 0.25 weight%. That's carbon. And we also know CS, which is 1.2 weight%. That's carbon as well. And we also know CX. Do we know CX? What's the CX in this equation? Yeah, that's a concentration we want to reach for this problem. We want to reach a high concentration inside of carbon, which is CX. CX should be 0.8%. That's our goal, to reach CX to 0.8%. That's also carbon. All right, now let's plug in those things into the equation. Let me move this picture here. Oops. No, it won't allow me to move that, but it's okay. CX minus CO divided by CS minus CO. This equals to 1 minus error function times, on the top for error function we have X, which is location. Here X is 0.5 millimeters. We want to make sure we use standard units. So we want to convert that unit to meters. What is the meters for 0.5 millimeters? Yes, so it's going to be 10 to the negative 4 meters. That's the location. It's divided by 2 times square root times the coefficient, which is 1.6 times 10 to the negative 11 meters squared per second times time t. Okay, now I forgot to plug in all the values on the left-hand side of the equation. Let's do that. 0.8 minus 0.25. On the bottom here, 1.2 minus 0.25. Okay. Can you simplify the calculation inside of the error function? So inside of this error function, we should get 6t2.5 divided by square root t. And on the left-hand side, if you do the calculation here, what's the number for that calculation? 0.8 minus 0.25, that's 0.55 divided by 1.2 minus 0.15. That's how much? That's 1.05. That should give you a number that's about 0.421. Okay, so now can we put that 1 to the other side of the equation? So through that 1 to the left-hand side of the equation. Oops, I think I made a mistake here. Yep. Here. Yeah, that 0.421 is already the number plus minus 1. So that's right. Oops. Okay. Once you simplify everything, you get this equation. The error function equals a constant, which is 0.421. Okay. Now it's time for us to learn how to solve error function. So error function, like I said, it's just a fancy math, and the value for error functions can be found from the table. So I have attached the table here. So this is our error function. The value of error function we know is 0.421. So what we need to do is go to the table for error function. That's the table right here above. It's also the table on your textbook. You can just Google it, error function table, and show you the similar table. So let's look at this table here. On this table, let's look at the head. We have Z and the ERFZ. So that tells us what is the corresponding value if we know Z. If we know Z, that we can read out what is ERFZ. Or another way we can do this is if we know the ERF, the error function value, we can look up the values under ERFZ and find that value, and we can find out what is corresponding Z. So in this case, let's go back here. We know the value of ERF, which is 0.421. Can we go to the table to find out where's 0.421? Okay. Where's 0.421 for the error function value? .421. So here, let's look at this line here. We have, okay, 0.42. And on the top, we have 0.379. So they are not very close to 0.421, but we know the 0.421 is in between these two numbers. So right now, we can kind of do an estimation. If you want to do a rough estimation, we look at the corresponding z value. We know our z value should be in between 0.35 and 0.4. So what does that tell us? It tells us what is inside of this error function, 62.5 divided by square root t, is in between 0.35 and 0.4. We can do a better job to predict, to estimate what's that value. So what we're gonna do is to look up table and use interpolation. You guys know how to do the interpolation? If you have table, if you have a plot, just pretty easy. It's you grab the value here. Okay. So here we're gonna use z as a variable we don't know. Let's assume this guy here. It's our value z. It's an unknown we're looking for. So z minus the smaller number, which is 0.35 on that table. That's on the top. On the bottom, we have the large number, 0.4 minus 0.35. So here, where's that 0.35 and 0.4 come from? That's come from the table. That's come from the table right here, 0.35 and 0.4. Since our z, it's in between these two numbers. So we're gonna use z minus the lower bound, but let's write it out. Z lower bound, that's 0.35. The upper bound, it's 0.4. So we're gonna use z number minus the lower bound, 0.35, divided by the difference between higher bound and lower bound. That's on our left-hand side of equation. On our right-hand side of equation, we use the values from the arrow function. Same deal. What is the corresponding value of the arrow function for our z? That's what we have up here. The corresponding arrow function value of z is 0.421. So we can put 0.421 there, minus, let's look at what is the value for arrow function for 0.35. That's on the table under arrow function. So that's a value which is 0.3794. 0.3794. Yep. On the bottom here, do the same thing. Find out the corresponding value for arrow function under 0.4 and use that value minus the value of arrow function when z equals 0.35. So when z equals 0.4, that is this value here, 0.4284. So let's plug in that, 0.4284 minus 0.3794. And now you can use your calculator to find out the more accurate estimation for z. From here, what's your calculation for z? Wait, say that again? That's a little bit off. So that Z value should in between 0.35 and 0.4. We just want to get a more accurate estimation. So it's a value in between 3.5 and 0.4. Anybody have a, do you have a different number? Try it. Gordon? Yeah, that sounds about right. It's about 0.39 something. So this is a more accurate estimation about what is Z. Okay. Okay, any question here? The reason we use interpolation is just we're engineers. We want to do a little better job on estimation other than just guess the value in between two numbers. It's totally fine if you just go to this table and kind of guess, okay, we know our value should in between 0.35 and 0.4, then you give it a random number in between, like such as 0.38 or 0.37. But it's just not as accurate as interpolation. Okay, so this is interpolation. How we find the Z. Remember here, Z, it's what is inside of that arrow function. So now we can use that Z number. Z equals 0.392 equals 62.5 divided by square root T. Now we have this equation. Can we find T? Try to use your, you can use your calculator to find out what is the T. You have a T? What's the time? 25,000. Yeah, that sounds about right. 25,400. The unit here, it's second. So second, it's a unit for this time. All right, it's pretty hard to understand how long is that time. Can we convert that to hours? Divide that by 3,600. That's about 7.1 hours. Right. So now we have the prediction on time, how long it takes for that bar at that location to reach 0.88% of carbon concentration. 7 hours. What do you think? Do you think it's pretty long or pretty fast? Compare that to your gas. It's not too bad. Okay. How about let's reduce that temperature to room temperature? So what if we reduce that temperature in this problem, which is right here, 950 Celsius. If we reduce that to 25 degrees, the room temperature, what's your estimation on the time it cost? It could take years, it could be. Okay, the temperature would change this value. Under room temperature, this value is going to be way smaller than 1.6 times 10 to the negative 11th. And if our diffusion coefficient becomes very small, let's look at how that change our calculation. So that's where is your diffusion coefficient. So that value can be very small. So in total, your error function value, instead of your error function, this whole value can be very large. So you will end up with a much longer time. Okay, how about let's do a practice. I think some of you may have questions on interpolation. Okay. Okay, let's do this. If the ERFZ equals, let's see, number here, 0. Okay. Equals 0.8999. Find Z. All right. I want you to write down, if we know the error function value equals 0.8999, and I want you to find out what is Z using interpolation from the method we just talked about. And here's the table for error function. So now our ERFZ equals 0.8999. I want you to do an estimation for Z. Use interpolation. Okay, raise your hand if you have you find out what is Z. What's your Z number? 1.1645. How about you? Okay. Okay, let's walk it through. That sounds like a reasonable number, just by looking at it. Okay. So now our error function value is 0.8999. Let's look at the table. Look under error function ERF values to locate where is the closest number to 0.8999. Okay, I found this guy here, 0.8802. So that's smaller than 0.8999. Another number here, 0.91. That's larger than the number we have. So the corresponding z is 1.1 and 1.2. So we know our z is in between 1.1, 1.2. Now we can do an interpolation. Z minus the lower bound number value of z, which is 1.1, divided by the difference of the upper bound and lower bound, which is 1.2 minus 1.1. On the right-hand side of the equation, we have the value for error function when error function z, which is 0.899, minus the error function value when z equals 1.1. That is 0.8802 divided by the error function when z equals 1.2. 19103 minus 0.8802. Okay, now you have an equation. Z is your only unknown. If you use your calculator, you can find out z, it's about 1.16. That's close enough. 1.16, which is a much better estimation of what is the value. Okay. All right, any questions on interpolation? And read this table. Okay, this table is probably only used for when we try to solve the fixed second law, right? When we have tons of assumptions, when we have that bar is infinite long, when we have a constant surface concentration, and we have a uniform initial concentration. So that solution, it's limited by tons of assumptions. But it give us a better understanding how fast things diffuse into another solid. Okay, now let's look at a situation how temperature would change our diffusion coefficient. So that's kind of important because temperature here would do a lot of things to our equation. So our diffusion coefficient, D, it's affected by temperature. D equals D naught times exponential negative QD divided by RT. Or if you prefer a different writing here, there would be D E times QD. That's exponential. Either way. Here, QD, have you seen QD before? QD is very familiar. QD, where do we learn QD? So QD here, it's called activation energy. Where did we learn activation energy? In which equation we learned there's an energy term? What is something related to energy? Vacancies. When we calculate how many vacancies in a unit volume, this guy showed up, QD. So QD has a unit of either joule per atoms or it's electron volt per atom. So it's energy. R here, it's a gas constant. The value is a constant. So it's either 8.31 joule per mole times Kelvin, or you can write that as a different unit, 8.62 times 10 to the 5th electron volt per atom Kelvin. T here is a temperature. It's absolute temperature in unit of K, Kelvin. So this equation tells us if we change temperature, then we're going to get a different diffusion coefficient. Here I didn't expand this. D naught here, it's a time independent pre-exponential. The unit is meter squared per second. So D naught here, it's a constant based on different materials. So it's a material property. Different metals will have a different D naught value. Okay, so that tells us if we know the temperature, if we know what is D naught, we can find out what is the new diffusion coefficient under that new temperature. Okay, let's do a practice. Let me see here. Maybe next time. All right. Okay, let's do the practice next time because we don't have enough time here. But now I want to show you this table. This is a table on your textbook as well. You can find that. This table shows different diffusion coefficient for different materials and different types of diffusion. First, I want you to look at the top. We have interstitial diffusion. Remember what's that? So when you have smaller atoms diffuse into the interstitial space, carbon steel is a very good example. That shows the diffusion species. Carbon diffuse into iron. Iron can be in different crystal structure, can be in BCC or FCC. Now you can see how our crystal structure can affect diffusion coefficient, because when you look at the value under D naught, when we have FCC structure, when it's alpha fifth, the D naught value is 2.3 times 10 to the negative fifth. But when you have BCC structure, that value it's much less. So you can look at if we switch carbon with nitrogen and how that change our diffusion coefficient. So that's just for interstitial diffusion. Now we can look at self-diffusion. Self-diffusion only occurs if you look at here. Why it's iron, copper, aluminum. Because it's called self-diffusion. Remember, self-diffusion only occurs in pure metal. So the pure metal atoms diffuse into the empty vacancy site. So that's why it's the same metal. On the bottom here, we have interdiffusion. That's two metals diffuse into each other. Here we have zinc diffuse into copper. That shows how fast, what's the diffusion coefficient. And also it shows other different atoms. One interesting thing I want you to look at, the first two lines here. The first one is zinc into copper. And the second line here, it's copper into zinc. Did you find something interesting? I want you to compare the value here. One is 2.4 times 10 to the negative fifth. Another one is 2.1. Okay, same metal, zinc and copper, but the direction is different. When direction of diffusion is different, the diffusion coefficient is different. So keep that in mind. It's not the same rate as copper diffuse into zinc. Which one is faster? If you have a copper diffuse into zinc, that diffusion coefficient is faster than you have zinc diffuse into copper. So it's direction dependent. Okay, that's all for today, and we'll see you guys on Friday.
Friday is on Moodle. I saw there's like a report due. Is that still?
Yeah.
Yeah.
That's a report for your, I think that's a water and carbon dioxide footprint for your materials. So you need to do research to find out what's those values and what's the impact on.
I believe you're my advisor now. I had that before.
Okay, yeah.
I actually signed up for the wrong advising time.
Where you want to sign up for advising time, or?
I would like to reschedule.
Okay. Yeah. Just go to my calendar, schedule another time that works for you.
Okay.
Yep.
More people probably didn't. So we just kind of assumed